In this lesson, we will learn about functions and their representations. Our lesson plan is as follows. First, we will discuss what a function is. Then we will look at different ways to represent a function. Each representation of a given function highlights different properties. Therefore, it is often useful to have more than one description of the same function to solve a problem. We will also look at possible symmetries of functions and define even and odd functions. At the end, we will closely examine a certain way of defining a function by piecing together several other functions. We think of a function f as a rule that assigns to each element x in a set A exactly one element y denoted by f of x in a set B. In this case, the set A is called the domain of the function f. A symbol representing an arbitrary element in the domain is called an independent variable. Here it is denoted by x, but any other letter could be used as well. A symbol which represents the value of f is called the dependent variable. Here it is denoted by y, but again we can use any other letter. For example, in physics, the velocity of a particle, depending on time, is denoted by v of t. Here t is an independent variable and v is the dependent variable. The range of f is the set of all values f of x, as x varies throughout the domain A. Note here that the range of f does not have to coincide with the set B. The set B is generally larger than the range and is referred to as the codomain of f. The sets A and B would be arbitrary. For example, we can define a function from a set of all living people into the set of natural numbers by mapping each person into his or her year of birth. In this course, however, we will typically consider functions for which the domain A is a subset of real numbers and B is all real numbers. A popular way to picture a function is by an arrow diagram. We have two sets. The set A consists of 4 elements, 1, 2, 3, and 4. The set B consists of 5 elements, 1, 2, 3, 4, 5. We indicate by an arrow that an element in the set A is mapped to the element in the set B. Here, 1 is mapped to 2, so f of 1 equals 2. 2 is mapped to 1, so f of 2 equals 1. 3 is mapped to 2, and 4 is mapped to 5. The domain of f is 1, 2, 3, 4. The range of f is the set 1, 2, 5. We did not include elements 3 and 4 into the range of F because no element in the domain is mapped into 3 or 4. We can represent F by a table of values. We write the elements of the domain on the left and corresponding values of the function F on the right. The same function F can also be described by a formula. For example, x squared minus 4x plus 5. If we plug in 1 for x into this formula, we get that f of 1 equals 1 squared minus 4 times 1 plus 5, which is 2. F of 2 equals 2 squared minus 4 times 2 plus 5, which is 1, and so on. We see from the previous example that we can represent a function in several different ways. First of all, we can simply describe the action of a function in words. If the domain of a function is finite, we can define a function numerically by a table which gives the values for each element in the domain. A function could be represented visually by a picture called the graph of the function. The most common way to describe a function in calculus is algebraically, by an explicit formula which tells us how to compute the value for each given argument. It is useful to have different representations of the same function to better understand the behavior of the function. Graphical representation visualizes at once key features of a function, such as, but not limited to, extreme points, increasing-decreasing behavior, zeros, and continuity. Such concepts and their importance will be discussed in depth later on. To be precise, the graph of f is the set of points f of x on a coordinate plane where x is in the domain of f. Here x attains all the values in the domain of f. This is the graph of f introduced in the previous example. It consists exactly of 4 points related to the 4 points in the domain. If we change the domain to include, say, all values between 0 and 4, we obtain a connected curve. Even though the equations which define these functions are identical, the resulting functions and their graphs are different due to the different domains. Not every curve in the xy plane is a graphical representation of a function. To determine whether a given curve is a graph of a function, we use the vertical line test. A curve in the xy plane is the graph of a function of x if and only if no vertical line intersects the curve more than once. Consider 2 curves in the xy plane. In the first example, this vertical line intersects the curve twice. This curve cannot represent a function of x, because a function cannot assign two different values to the same point x equals a. In the second example, any vertical line intersects the curve only once. So each point on the x-axis has at most one corresponding value on the y-axis. This curve does represent a function. Although graphical representations are very useful to visualize a function, no picture can exactly define every point in an infinite set. Therefore, we often use an algebraic description by a formula that tells how to compute the value of the function for a given value of the argument. The same function could be represented by different formulas. For example, f of x equals x squared minus 1 and g of x equals x minus 1 times x plus 1 defines the same function. Suppose a function is defined algebraically and its domain is not specified. Then we assume that the domain is a set of all real numbers for which the formula makes sense. This set is referred to as the natural domain of a function. For example, if f of x equals 2x plus 1, we can plug in any number for x. So the natural domain of this function is all real numbers. Now let's look at the function 1 over x minus 2. The domain is all the values that x is allowed to take on. The only problem we might have with this function is division by 0. The only value of x which makes the denominator 0 is 2. Therefore, the domain of this function is all real numbers except 2. Now let's look at the function a radical x. Since we cannot take square root of a negative number, we need to exclude all negative numbers from the domain. So the domain is all non-negative real numbers. You have to remember that there are two most common reasons for limited domains. The first one is the issue of division by 0. If a function involves a fraction, you need to find all values of the independent variable which makes the denominator 0 and leave those values out of the domain. The second reason is that we cannot have negative numbers under even radicals. Here you need to be careful. We can have negative numbers under odd-powered radicals, but not the even ones. For instance, a cube root of negative 8 is negative 2, but a square root of negative 8 is not a real number. So if a function involves an even radical, you need to make sure that the expression under the radical is non-negative. Let's take a look at a few examples. The first example is to find the domain of f of x equals 5x plus 3 divided by 2x plus 1. The denominator cannot be 0, so we set 2x plus 1, which is the denominator, not equal to 0. We subtract 1 from both sides and get 2x is not equal to negative 1. Now divide the expression by 2 and get that x cannot be equal to negative 1/2. Therefore, the domain of f is all real numbers except negative 1/2. We write it in interval notation. Domain is the interval from negative infinity to negative 1/2 union interval negative 1/2 infinity. Parentheses here indicate that we do not include the endpoint negative 1/2 in the domain. The second example is to find the domain of f of x equals radical x minus 2. The expression under the radical has to be non-negative, so we set x minus 2 is greater or equal to 0. We add 2 to both sides and get that x has to be greater or equal than 0. In the interval notation, we write the domain as an interval from 2 to infinity. Square bracket here indicates that the endpoint 2 is included in the domain. The third example is to find the domain of f of x equals 7x plus 11 divided by x squared minus x minus 6. The denominator cannot be 0, so we set x squared minus x minus 6 not equal to 0. We factor the expression x squared minus x minus 6 into x plus 2 times x minus 3. Since x plus 2 cannot be 0, x is not equal to negative 2, and x also cannot be 3, since x minus 3 cannot be 0. The domain of f is all real numbers except negative 2 and 3. We write it in interval notation. Negative infinity to negative 2, union negative 2, 3, union 3, infinity. Again, parentheses here indicate that negative 2 and 3 are not included in the domain. The fourth example is to find the domain of f of x equals cube root of x minus 5 plus 3x minus 1. Since we can take a cubic root of any number, there are no restrictions on x, so the domain of f is all real numbers. We write it again in interval notation. This is an interval from negative infinity to infinity. It is natural to ask whether functions with symmetric domains are actually symmetric as graphs. So if there is a curve on xy plane, what type of symmetry can it have? A curve can be symmetric about the y-axis. In this case, the left half of the plane looks like the mirror image of the right half of the plane. A curve can also be symmetric about the x-axis. In this case, the bottom half of the plane looks like the mirror image of the top half of the plane. And finally, the curve can be symmetric about the origin, when the left half of the plane is an upside-down mirror image of the right half. These are three possible symmetries for a curve on a plane. However, if you look at the middle picture and apply a vertical line test, you see that this line intersects the curve in 2 points. Therefore, this curve does not represent a function. Since the symmetry about the x-axis is not possible for graphs of functions, we concentrate our attention on the other two symmetries. Let's look at the left picture. Suppose a graph of a function f is symmetric with respect to the y-axis. If we take two symmetric points on the x-axis, x and negative x, the corresponding y values have to be also the same, since the points on the graph are symmetric. Thus, f of negative x has to be equal to f of x for every point x. The functions with this property are called even. F is an even function if for every x in the domain, negative x is also in the domain of f, and the value f of negative x equals to the value f of x. Now let's look at the right-hand side. Here the graph of a function f is symmetric with respect to the origin. If we again take two symmetric points on the x-axis, x and negative x, the corresponding y values have to be also the same in absolute value, but the opposite sign. Therefore, we have f of negative x equals negative f of x. Functions with these properties are called odd. F is an odd function if for every x in the domain, negative x is also in the domain, and f of negative x equals negative f of x. Let's determine whether function x squared minus 3 is even, odd, or neither even or odd. We plug in negative x instead of x. F of negative x equals negative x squared minus 3, which simplifies into x squared minus 3 because negative 1 squared gives you 1. X squared minus 3 coincides with f of x. Therefore, this function is even. We can confirm it by graphing f of x you can see on the graph that the curve is symmetric about the y-axis. Okay, let's look at the function x cubed plus 5. Is it even, odd, or neither even or odd? Again, we plug in negative x instead of x and simplify. F of negative x equals negative x cubed plus 5. Since negative 1 cubed is again negative 1, this simplifies into negative x cubed plus 5. This expression is not the same as the original function f of x. We try to factor out negative and obtain negative x cubed minus 5. The expression in parentheses is not equal to the original function. Therefore, this function is neither even nor odd. Again, by graphing the function x cubed plus 5, we see that it is not symmetric about the y-axis, and it is not symmetric about the origin. We can modify this function slightly and consider x cubed plus 5x. We plug in negative x instead of x and obtain f of negative x equals negative x cubed plus 5 times negative x. This simplifies into negative x cubed minus 5x. If we factor out negative, we obtain negative 1 times x cubed plus 5x. The expression in parentheses is exactly the original function, so this equals negative f of x. This means that this function is odd. Let's graph it. You see that the graph of x cubed plus 5x is symmetric with respect to the origin. Quite often in practice, we cannot describe a given function by just one formula on the whole domain. If a function f is defined by different formulas in different parts of its domain, we say that f is piecewise defined. For example, consider f of x equals x squared minus 5 if x is less than 1, and x minus 2 if x is greater or equal than 1. Let's evaluate f at several different points. To find f at negative 1, we first look at the argument. Here x equals negative 1, which is less than 1. For any x less than 1, f of x equals x squared minus 5. So we plug in negative 1 into x squared minus 5. We get negative 1 squared minus 5, which is negative 4. Now let's evaluate f of 2. Here x equals 2, which is greater than 1. So we plug 2 into the expression x minus 2. We obtain 2 minus 2, which is 0, so f of 2 is 0. And the last example, let's evaluate f of 1. x is equal to 1. So again, we need to plug in 1 into the second expression. We get 1 minus 2, which is negative 1. So f of 1 is negative 1. How do we graph f of x? We notice that for x less than 1, f of x is x squared minus 5. So the graph of f to the left of x equals 1 coincides with parabola x squared minus 5. And here it is. The graph of f to the right of x equals 1 coincides with the line x minus 2. Since f of 1 equals negative 1, point 1 negative 1 is marked by a solid dot, and point 1 negative 4 is marked by an open dot to indicate that it does not belong to the graph. Another example of a piecewise defined function is the absolute value function. The absolute value of a number x is the distance from 0 to x on the real number line. Distances are always positive or 0, so we have that the absolute value of x is greater or equal than 0. For example, the absolute value of 2 is 2 because the distance from 2 to 0 is exactly 2 units. The absolute value of negative 5 is 5 because the distance from negative 5 to 0 is exactly 5 units. Finally, the absolute value of 0 is 0, since the distance from 0 to itself is 0. In general, the absolute value of a number x equals negative x if x is less than 0, and x if x is greater or equal than 0. Recall that if a number x is negative, then negative x is positive. The graph of absolute value of x consists of two line segments. It coincides with the line of slope negative 1 to the left of 0 and with the line of slope 1 to the right of 0. And here you can see the graph. This is the end of our lecture. In this lesson, we will learn about functions and their representations. Our lesson plan is as follows. First, we will discuss what a function is. Then we will look at different ways to represent a function. Each representation of a given function highlights different properties. Therefore, it is often useful to have more than one description of the same function to solve a problem. We will also look at possible symmetries of functions and define even and odd functions. At the end, we will closely examine a certain way of defining a function by piecing together several other functions. We think of a function as a rule that assigns to each element x in a set A exactly one element y, denoted by f of x, in a set B. In this case, the set A is called the domain of the function f. A symbol representing an arbitrary element in the domain is called an independent variable. Here it is denoted by x, but any other letter could be used as well. A symbol which represents the value of f is called the dependent variable. Here it is denoted by y, but again we can use any other letter. For example, in physics, the velocity of a particle, depending on time, is denoted by v of t. Here t is an independent variable, and v is a dependent variable. The range of f is the set of all values f of x as x varies throughout the domain A. Note here that the range of f does not have to coincide with the set B. The set B is generally larger than the range and is referred to as the codomain of f. The sets A and B could be arbitrary. For example, we can define a function from a set of all living people into the set of natural numbers by mapping each person into his or her year of birth. In this course, however, we will typically consider functions for which the domain A is a subset of real numbers and B is all real numbers. A popular way to picture a function is by an arrow diagram. Here we have two sets. The set A consists of 4 elements, 1, 2, 3, 4. And the set B consists of 5 elements, 1, 2, 3, 4, and 5. We indicate by an arrow that an element in the set A is mapped into an element in the set B by a function f. Here 1 is mapped into 2, so f of 1 equals 2. 2 is mapped into 1, 3 is mapped into 2, and 4 is mapped into 5. The domain of f is the set A, which is 1, 2, 3, 4. The range of f is 1, 2, and 5. We do not include 3 and 4 into the range because no element from the domain is mapped into 3 or 4. We can represent f by a table of values. We write the elements of the domain on the left and corresponding values of the function f on the right. The same function f can also be described by a formula. For example, x squared minus 4x plus 5. If you plug in 1 for x, we get 1 squared minus 4 plus 5, which is 2. If you plug in 2 for x, we get 1, and so on. We see from the previous example that we can represent a function in several different ways. First of all, we can simply describe the action of a function in words. If the domain of a function is finite, we can define a function numerically by a table which gives the values for each element in the domain